This lecture is about a technique which is very popular in industry, biotech, biopharma, to some extent the food industry as well, in terms of characterizing macromolecules in terms of the molecular weights and conformations and things. It's more popular than the ultracentrifuge because it's easier to operate, it's less expensive, but there are some pitfalls and limitations that come with this methodology, which you need to be aware of. So if you encounter this in your future careers, which you probably will do, if you go into the biopharma or food characterization areas, then this is an important methodology, and it comes up in patent cases and things where people want to know whether they're inside or not inside someone else's patent. It's a way of characterizing molecular weights, molecular weight distributions, and conformations of molecules above a molecular weight of 2,000–3,000 and up to several million, including antibodies and including glycovaccines, including excipients, all this sort of stuff. This is a very popular method now. Light scattering, or MALS, when you couple light scattering to gel chromatography or size exclusion. What's happened here? Chromatography. SEC MALS, go away. This black bar. It's better. Okay. Light scattering MALS. So we need to understand how this operates to a limited extent. We have to go into great detail, but enough to understand how it works and what the sort of molecules you can look at, what the limitations are, and the information that it can give. So basically shining a laser light through a solution of your molecule or macromolecule, and you're measuring the light scattered because of the absorption, re-emission of light radiation by the macromolecules, and you measure this scattering as a function of angle and also concentration. You can get lots of wonderful information out. So it's very simple in principle. You have a light source, this is usually a laser these days, which shines light through a solution of your macromolecules, your albumins, pectins, or your tomato bushy stump viruses, your xanthans, whatever you like, antibodies, Martian rock lizard protein, no. And you measure essentially the light scattered, or the intensity of light scattered, as a function of the scattering angle theta, which is the angle between the direction of the incident beam to the direction of the, or wherever your detector is. So the photometer detector, that angle theta is called the scattering angle. Scattered intensity I, angle theta, and this is the original intensity I naught, and this is the intensity at zero angle that's left after scattered light has taken some of the original intensity away. So this is a bit like a spectrophotometer in a way, because with a spectrophotometer you measure the transmitted light intensity compared to the instant light intensity, except the difference between absorption and scattering is that absorption is the absorption of light, UV light usually, because of the existence of chromophores in the molecule. Tryptophan, tyrosine for proteins, for example. Scattered light is light which is absorbed and re-emitted at the same wavelength and the same energy. When it's re-emitted at a different energy, a lower energy, that's called fluorescence. Yep, spot on. So we would do that in the structural biology module next term. If you do that, ABI students, ABT, no choice in doing it, whether you like it or not. MRes, don't know, no, exempt. Erasmus, exempt. That's where they're smiling. But they're missing a great module. It really is great. Right, so there are two main types of light scattering. One is so-called classical light scattering, where you measure the scattered intensity I theta as a function of scattering angle theta. And from the way the intensity changes in angle, we can get information like the weight average molecular weight. And we can also get this friend here. Remember the rate of duration we talked about before, but never actually mentioned how we measure it. Well, light scattering is one of the methods for getting it. There's X-ray scattering as well from solutions. So we can get the RG, provided the particles aren't too small. If they're smaller than, probably an antibody molecule is right on the lower limit of the molecular weights where you can get an RG from light scattering. What's the molecular weight of an antibody molecule? No, we haven't done antibodies yet, but roughly. It's about 3 times that of our favourite molecule. 150,000. Yeah, of albumin's about 45,000. Yeah. You're thinking of hemoglobin. About 150,000. Anything below that, we have to use X-ray scattering rather than light scattering to get the RG out. And there's a second type of light scattering called dynamic light scattering, where you don't measure the total intensity as a function of angle, but you measure the fluctuations in intensity at a given angle, because the particles are moving about. You know, they don't stay put. They're moving about due to think of a dark colour.
Brownian motion.
Yes, I was going to say value of 4 points on the Snoop table. Brownian motion, yeah. And the smaller molecules tend to move faster than the bigger ones, so we can use dynamic light scattering, which measures something called the diffusion coefficient, which measures how fast particles move about, and that can be related to the particle size. So we do dynamic light scattering in the structural biology module next semester. This is probably convincing ABI students to choose the bioinformatics module instead of structural biology. But no, that's the second type, which is also extremely popular in particularly in the biopharma industry. And it's also used as, because it's quite rapid, it's also used as a monitor for protein crystallization. You know, part of the problem with protein crystallization is to try to find the right combination of conditions to get proteins to crystallize. And dynamic light scattering is quite good at seeing if there's a change in size of a system. If something starts to grow, then DLS is a good probe for that. So it's a good check for protein crystallization. Besides being it's also relatively inexpensive compared to MALS and ultracentrifugation. So this is extremely popular. industry. In fact, when we did the concentration demonstration, we've all done that now, haven't we? The concentration demo practical. The computer we were using was actually hooked up to one of the dynamic light scattering instruments in that lab, a small sort of, two of them, beige colour instruments. Okay, but that's the next term. We're going to focus on classical light scattering, which is measuring the intensity, not how it changes, but the intensity, not how it changes in time, intensity and how it varies with angle. Classical light scattering. So not dealing with fluctuations through movement. That's dynamic light scattering. We're dealing with just the steady state intensity as a function of angle. Okay, so molecular weights and RGs. Right. So a bit of background. Man with beard. I could show any man with beard and say it was Maxwell, because that's what they all tend to have in the 19th century. James Clerk Maxwell, and I think, was he the first professor? Was he the first Cavendish professor in Cambridge? I think he was actually. I think Maxwell was the first Cavendish. There's another one. This is, who's this? Oh, you've got it up on the screen. That's right. That's why it's much better with overhead. These are basically overhead transparencies which are transferred to this. And much better with overhead transparencies because you just put the picture up, and who is this, and then you put the name as an overlay. This all stores that. I think did it do it with Svedberg? Yeah, I did it before I gave you the handouts, but if you'd already got that up on screen like you do, it's as bad as the vets. The vets are always. You go to a lecture theatre with vets in there, every single person's got a laptop out. So, yeah. Unlike the classical paper and pen, which I think is much better, with no handouts. You've got to admit, I've been very good on handouts. Yeah. Against the university, I've got to watch this recording. Against the university directive is not to give handouts. You know that, which we've been told not to give handouts. Yeah. So a great personal risk to me. So this time I haven't done handouts, so sorry about that. So Lord Rayleigh, and these are the two key people. If I cut up all the history, I have. Okay. What I used to do is give a bit of a historical review of light scattering. Essentially, the phenomenon of light scattering was known for a long time, and it was Tyndall, the Tyndall effect, where you can see if it's a foggy, dank day, and you're looking down the high street, and there's a bus coming towards you, not directly at you, but towards you, with its headlights full on, and then you can see the light scatter in all the haze. That's because of all the moisture droplets which are scattering the light everywhere. This is called turbidity. It's a phenomenon of light scattering, light being absorbed and re-emitted in all directions. And so light scattering phenomena was known about, and it was really a combination of Maxwell and his electromagnetic theory. We had to do all this because I did my degree many years ago in physics, so we had all this Maxwell, all the electromagnetic equations, the Maxwell equations and things, how to solve them. So Maxwell is the father of electromagnetic theory, and it was Lord Rayleigh who took Maxwell's theory and applied it to the scattering of light, and was able to show phenomena like, why is the sky blue? It's because blue light, or the higher energy wavelengths, are scattered more than the lower wavelengths, the red colour, by the particles in the atmosphere. So why the sky blue and why sunset's red is all to do with Rayleigh's theory, which is based on the electromagnetic theory of Maxwell. But then Einstein tends to poke his finger in many pies. It was Einstein and also Rayleigh who developed the theory for light scattering by solutions of molecules. And other people like Gans, Debye, got a Nobel Prize, and me, who contributed, along with many others, to the development of the light scattering by particles in solution. When we're dealing with scattering of particles in solution, including macromolecules, there are three categories. The so-called Rayleigh, that's with a Y, okay? If you leave the Y out, you end up with the bicycles, okay? The rally. In fact, the business park where the Abbey students all go to on the the Jubilee campus. That's all part of the old rally works. Yeah. And so nothing else to do with Sir Walter Raleigh. Sir Walter Raleigh is the guy who put his coat on the floor for Queen Elizabeth. Yeah. Also, it seems. I'm thinking of Francis Drake. Francis Drake was the one who travelled. Yeah. So Walter Raleigh was the gentleman. Again, nothing to do with Rayleigh, whose real name was actually Strutt. And actually, Strutt's quite a big name in the East Midlands area. You'll see Strutt's name appear in lots of different places, particularly around the Derbyshire area. So, good local name. Lord Rayleigh. And Rayleigh scattering is when the particles have their maximum dimension, which is less than a 20th of the wavelength of light. So if you've got laser light so you've got red laser light of wavelength approximately, I know that. What's the wavelength of red light? No, not come across that one. It's about 600 nanometers, okay? So if the particles are of 30 nanometers or less, then we regard them as Rayleigh scatterers. So for lysozymes, myoglobins, again there's a misprint, no of albumin, of less than, that's probably a very generous, or very overestimate, probably less than 140,000 rather than 40. So I'd slip an extra one in there. That would be regarded as Rayleigh scattering. And the theory is very simple. Well, in comparison with the rest. Then we've got Rayleigh-Gans-Debye theory, RGD. And this corresponds to where the dimensions of the particle are between a lambda over 20 to lambda. So particles up to the size of several hundred nanometers. So in this range This is called the Rayleigh-Gans-Debye range. And the other condition for Rayleigh-Gans-Debye scattering is that the ratio of the refractive index of the particle to that of the surrounding medium, aqueous medium, N0, minus 1 should be much less than 1. So with that condition, and that condition, this is known as Rayleigh-Gans-Debye. This is of most interest to us, really. This and Rayleigh scattering. When you get to particles, bigger than the wavelength, such as large viruses, bacteria, bacterial spores, all this sort of stuff, then it's a different type of light scattering called MALS scattering. And the theory is very complex. So we need to know a little bit of theory, only a tiny bit, in order to understand this process. And it's basically Rayleigh-Gans-Debye, and the Rayleigh scattering is a limit of this. So Rayleigh-Gans-Debye for particles between 40,000 to about 20 million. And that includes really most of the molecules of interest to us. I mean, antibodies, glycovaccines, all that stuff, xanthans, pectins, all these things, are all within this range. So we define a parameter known as the Rayleigh ratio, which is the ratio of the intensity of light at angle theta, zoom, okay? So the intensity of light scattered at angle theta to the incident intensity I0. Where are we? And there's this geometric correction factor as well, which only applies if we're not using laser light. If we're using laser light, and I can't go into the theory behind this, but if we're using laser light, it's just I theta over I0. If we're using conventional light, then we have this extra term here involving the square cosine of theta, cos squared theta. And light scattering by a solution of macromolecules is summarized by this equation here. I mean, it looks complicated, but there's nothing in here which we haven't met before. So C is the concentration, R theta is the Rayleigh ratio, the intensity scattered at an angle theta divided by the incident intensity. Lambda is the wavelength, theta is the scattering angle, Rg is the gyration radius, 1 over m, molecular weight, 2b or not 2b? It's 2b. Okay, so it's like the centrifuge. 2b. Rather than not 2b. C is the concentration, so that's fine. And a couple of things here. If we work at a very low angle, so low angle, small angle, if theta equals 0, what's sine theta? 0, yeah. If theta is 90 degrees, sine theta is 1, yeah. Good. So if we work at a very low angle, where this is close to 0, and it's divided by 2 anyway, so that's good, then if that's 0, then all this lot is 0. So this just comes kc over r theta equals 1 over m plus 2 bc. That's right. And also, if we work at a very low concentration, C becomes close to 0. Yeah, and if C is close to 0, this lot becomes close to 0. So kc over r theta equals, or about 1 over m. Yeah. So if we work at low angle and low concentration, then we just get the molecular weight out dead easy. If we can work at low angle and if the concentration is low enough. Doesn't always work that way, I'm afraid. Because at low angles you get all sorts of problems because of dust. Any bits, any little bits and things in there, it scatters like mad at low angle. So can't always do it, and we can't always get to a low enough concentration, because the lower the concentration, the lower the signal you get, and sometimes you can't. Yeah, it's just too noisy. So sometimes you've got to work at higher concentrations and higher angles. K is just this collection of constants here. Avogadro's number, wavelength, the refractive index of the solvent, and dNdc, which is it's the same as, remember that parameter R we had when using refractive index to measure concentration? We call that the refractive increment. Okay, when we're using light scattering, we don't call it R, we call it dNdc, because R is something else. Okay, dNdc is a change in refractive index with concentration. So what's the refractive increment for proteins? Yeah, because I know you've all started revising your old stuff from BT7 or 4F7. The refractive index increment for proteins was about that's so easy, it's not even worth an answer. You see, so insulted by the trivialness of that question, is that right? Yeah, yeah, for proteins it's about 0.19 mils per gram. And for polysaccharides it's about 0.15. So for glycoproteins it's about 0.1, depending on the degree of glycosylation. Good, yeah, so we're getting it, yeah. There we are. So if B is known or C is small enough, then that is 0. But in cases where you can't do that, where you can't go to low concentrations because you don't get enough signal, or we can't work at very low angles because it's just too noisy, we have to make measurements at different angles and different concentrations, and what do? Extrapolate back, yeah. Extrapolate to 0 concentration and extrapolate to 0 angle. Yeah. Now this bloke here, skip that. This bloke here, Zim, he had this great idea of doing extrapolations on the same. Yes, boiling, isn't it? It's freezing out there. Boiling. Someone's really put the heating on. It's like Mediterranean. And I got 2 pairs of socks on this morning. Yeah. Anybody else got 2 pairs of socks? Yes. You got yourselves water bottles yet? Not yet. Good purchase. Yeah, but make sure when you get them, you don't put boiling water in. Because you wake up in the morning with blisters all over you. Okay, I've been there. Right, good. Actually, that's a good idea. Good idea for Secret Santa. Water bottles. So everyone's going to have water bottles this year. Ivy, yeah, Wilkinson's. Yeah, Wilkinson's is a good place to go to, actually, in Loughborough. There's good things there for a few quid. Right.
Halls tend to be quite warm anyway.
So what, forecast warm?
No, the halls. I don't
Oh,
know
the
about
halls are
these
warm,
halls,
yeah.
but halls in general tend
Yeah.
to, I don't know why, but they tend to be absolutely roasting.
So Bruno Zim, you came up with this idea of a plot, which is called a Zim plot. Yeah, there you go. It's clever. It really is clever. Let's just rotate it. Rotate clockwise. There we are. So this looks complicated. What all this is here is you plot Kc over r theta on this axis, and you plot c on this axis. Well, it's sine squared theta over 2 plus this constant times c. This constant is just to spread the data out. It's just an arbitrary constant. So you've got sine squared theta over 2 and kc on this axis and kc over r theta on this axis. And the idea is that you take 3 or more concentrations. This is 0.00041 gram per mil, which is in mg per mil, 0.41. 0.00081 gram per mil, which in mg per mil is 0.81, and 0.0112 gram per mil, which is 1.12 mg per mil. So 3 concentrations, and for each concentration, you make the measurements of this, what's this light scattering intensity. That's what you're measuring. You measure the intensity with your detectors at all these different angles. Okay, so you get your intensity I, theta, and then you divide it by the total intensity which the instrument records, and then you put that on the bottom, and you put the concentration on the top, and this constant which depends on the wavelength. What else was in there? We mentioned which had the NDC, that's right, yes, the NDC squared, that goes in there. So you just make measurements of the light scattering intensity, a number of angles for each concentration, and then you plot them on this special graph. And what you're doing is you're extrapolating for each concentration, you're extrapolating the results to 0 angle. This concentration, you extrapolate the results to 0 angle. So this concentration, extrapolate results to 0 angle. Yeah. And then you can go this way. For these concentrations, for each angle, you can extrapolate the results to 0 concentration. This one, this angle, 90 degrees, extrapolate the results to 0 concentration. So you get these 2 lines. That's a 0 concentration line, and that's a 0 angle line. All right? And because that's 0 angle line, all that RG squared rubbish, that goes out. You're left with that. Because this is a 0 concentration line, the 1 plus BC, all that rubbish, just ends up as 1. So the equation of this line is just that, and the equation of that line is that. So what's the intercept of this line? Intercept is 1m. And what's the intercept of this line? 1 rem. Yeah, so you've got a double extrapolation, so you can check to see if things are right. They should both give the same answer. And then from the slope of this line, we can get RG. Obviously, we've got to do some, manipulations. We've got to calculate, correct for that. The slope of this line is basically 16 pi squared over 3 times RG squared over lambda squared. That's the axis number, that's the x value. And the slope of this line is to be or not to be? That is the question. The answer is to be. They are, so it's, yeah. So that deserves a Nobel Prize, doesn't it? You didn't get one. No. No. So Zim, I met Zim when we got the, it's 50 minutes left to go, folks. Not quite there yet. When we got the, yeah. Have you all seen our MALS instrument? You know when we did the concentration stuff, there was the dynamic light scattering instruments on your right. On the other side was the MALS apparatus. We got the first one in Europe in 1989, and as part of the deal, one member of the lab got the chance to go to Santa Barbara in the USA to have a so-called training session on this instrumentation as part of a light scattering conference. So we had a discussion, and we decided it was me who went across to Santa Barbara. Yeah, that's right, isn't it? And Zim was there, Bruno Zim. And I went there thinking that Zim would be some very old man, because he did this work in the 1940s. The Zim plot was 1949, I think, when it was invented. So I thought, oh, this guy must be 120 or something. This quite youthful chap in his 60s, with training shoes and things, was there, which meant that he must have been, when he worked out this plot, he must have been in his early 20s. Yeah, so come on, guys, you do something like that. No, very clever man. He sadly died a couple of years ago, but it was a great honour to meet the big man himself. That's the Zim plot. In practice, if we can work at very low concentrations, then we do that. And in fact, the modern light scattering instruments are very sensitive that we can work at very low concentrations. So normally, these days, we don't have to do the concentration extrapolation unless we're dealing with very non-ideal systems. And that applies to our instrument in the Limes building, which is fortunate, really. So we can work at very low concentration. And that's an advantage in some ways over the sedimentation equilibrium technique, because we can't go below, much below 0.5 milligram per mil with the ultracentrifuge method, whereas with light scattering we can go below that, especially with big particles. That's Zim. What are we doing now? What's happened here? So if we clockwise, we need to counterclockwise. Right, conformation analysis. The RG, which we get from the slope of the angular plot. So why might these alternative techniques, X-ray scattering, neutron scattering, be more suitable for smaller biomolecules, molecules less than 40,000? Well, I think less than 140,000 really. That's what we find. Why do you think X-ray scattering and neutron scattering are better than light scattering for very small particles? That's right. The wavelengths are much smaller. So when we get to much smaller wavelengths, then it's very easy to satisfy this criteria for macromolecules. Same with neutrons. And if we do structural biology, then we will do X-ray scattering in the next semester. We've done this, haven't we? The gyration radius calculation. I'm not going to repeat all this. This is done in BT7, so apologies to Laura. Laura, you can do this, did you? No.
Okay.
So it's the RG is the root mean square distance of the mass elements in a particle from the center of the mass. It's a measure of the distribution of mass within a particle. And the RG has to be less than the overall dimension unless you have a ring structure where all the mass is on the outside of the protein. You never get that. It's usually distributed more or less uniformly. So the RG has to be somewhere between the center and the outer radius. And for spheres, uniform spheres, the RG is square root of 3/5 times the radius. For a rod-shaped molecule, RG is the length of the molecule. So for a myosin molecule or a long rod-shaped schizophyllum, molecule, or even xanthan, which is quite rod-shaped, the RG is the length divided by the square root of 12. And for ellipsoids like ovalbumins and all these sort of things, then it's a squared plus b squared plus c squared divided by 5 and the square root of that. When a equals b equals c, we have a sphere. That's 3r squared over 5 square root. So that's just that. Just take the square root of r squared is just r. And if you prolate c equals b and oblate c equals a. Random coils, so poollands, dextrans, all these sort of things. It's the square root of the root mean square end-to-end distance of the molecule divided by the square root of 6. And for big models, we can work it out, but it's complicated. So that's all you're getting for that. Some complicated function. What do you mean? These are all complicated. So you mean even more complicated. So some even more complicated function. Is that more correct? Or some not quite so easy as these function. Here's some typical values. Again, a misprint. The Waldman's not on here. But these are sort of values you get for globular particles, including this is not the tomato bushy stunt, but a related virus called turnip yellow mosaic virus. 5 millimolecular weight, 30 nanometers Rg. And then with these different shape molecules, myosin, rod shape, and DNA, which is a semi-flexible coil molecule, some examples. Okay, so now you know what sort of RGs to expect. Gyration radii. Right, to finish off with, what are those? What's one of those? What activity is happening here? Chromatography. Yeah, column chromatography. The guy call it gel permeation chromatography or size exclusion chromatography. As you see, it's the same thing really, because it's moles of gel excluding. So this is what guys on there. You've got a gel, a porous gel, obviously something lets material through. Not a solid gel. That wouldn't do, would it? It would just fill up and spill over. So it's got to be a porous gel. And you've got buffer, which passes through here. And then you apply a sample, which is dissolved in the buffer, and the sample macromolecule is washed through the gel to a fraction collector, which records the molecules appearing at this end. And as Guy explained, you tend to find that the larger molecules tend to be excluded from the pores of the gel, so come through faster. So it's the opposite to gel electrophoresis, where the larger particles are inhibited and come through more slowly because of the STS rod shapes. Here, with gel chromatography, the larger molecules are excluded from the column and come off before the smaller molecules. So it's a nice way of separating the molecules. And indeed, if you calibrate the column by putting down molecules of known molecular weight down the column and working out what volumes they come out on, solution volumes, and then putting your unknown down and seeing where that one comes out. So say if that's large molecule, think, say if that was thyroglobulin, okay, 700,000 molecular. No, let's say it was a BSA of molecular weight 68,000, and that was myoglobin of molecular weight 18,000. Then we put our unknown molecule, and it came out here. That means it's got a molecular weight between 60,000 and 18,000. And if we calibrate the column with more than two molecules, with lots of different molecules, we can then estimate the molecular weight of our unknown molecule. That's calibrated gel chromatography. Did Guy mention that? He did. He mentioned K-Alps and all this sort of stuff. Yeah. That's okay, so long as your calibration standards have a similar conformation to the molecules which you're trying to find out. So if you're trying to work out the molecular weight of a globular protein, then you would use globular protein standards. Because the separation on the column depends not only on molecular weight but also on the shapes. You've got to use, if you're working with polysaccharides and things, that's difficult because the conformations are all over the place. And you don't know what standards to use. So it's very difficult. I mean, in the industry, they tend to use what's called Poilouland standards. Poiloulands are random coils. So when they quote molecular weights, which have been calibrated by Poiloulands, they have to say the molecular weight is this, calibrated by Poilouland. So it's relative to Poilouland. So that takes the precaution if your conformation is different, then as long as you say it's relative to a Poilouland standard, that's okay. It won't be the real molecular weight because the conformation may well be different. So the solution is to stick the column or connect the column to a absolute molecular weight measuring device, such as, which doesn't absolute means doesn't require any calibration, such as what we've just been talking about, light scattering. Yeah, so you couple chromatography to light scattering. By the way, if you were using chromatography by itself, how would you know the protein is coming off at these particular points? What detector would you use to show where your, if it was a protein, yes, or what's the other concentration detector we talked about? refractometer. Yeah. So you use a refractometer or a spectrophotometer online to, this would go to a spectrophotometer or a refractometer. Why is the refractometer better? Because it's cheaper? No. Because it will detect any molecule, not just proteins. Yeah. So what we do is we connect a, rotate clockwise. Look at that. Reduce size. Is that suitably reduced? There we are. So, isn't that cool? So this is the elution profile with a refractive index detector for of albumin. Okay. So that's the elution volume from the column. So the bigger the molecule, the less elution volume is needed to get it from the column. In this case, it's required, what's that, about 19 mils to shift the albumin. And there's a bit here, a little bit here, probably a dimer or something. That's the albumin. So it's come from the column directly into a refractive index detector. But also in there is a light scattering detector. And this is a multi-angle laser light scattering, a multi-angle light scattering device, which measures the intensity at a variety of angles of the solution. And this is the intensity actually at the angle of, what's that say? 90 degrees. That's scattering at 90 degrees. And you can see it lines up beautifully with the concentration signal. That's the intensity. That's the concentration. So intensity, concentration, angle, you can get the molecular weight, Kc over R theta. Yeah. And if it's small enough, we don't have to do the angular extrapolation to 0. That's a 10 mg per mil. But the other thing about light scattering and chromatography is you load 10 mg per mil onto the column, but what happens to that 10 mg per mil? You've got buffer eluting through. It dilutes it, that's right, yes. So it dilutes it by a factor of 10 or so. So it means that we're at low concentration, so we don't have to worry about virial effects. So it's quite a cool method. And it was developed, well, the multi-angle light scattering was developed by Wyatt Technology in the 1980s, and we got the first one in Europe. Long story, which I won't tell you about. Rotate counterclockwise. There we are. Bit disappointing, it box. Modern instrumentation boxes. Not exciting. Yeah. Not like the old days. So this is what's called a light scattering multi-angle. We used to call it multi-angle laser light scattering, but now all light scattering instruments are lasers, so it's just multi-angle light scattering photometer. And operating at 658 nanometers, which is in the red. Yeah, so about wavelengths now, red. And 120 milliwatts. Take the lid off them. That's interesting, isn't it? You can't really see that well because it's light. I'm too lazy to turn the lights off. No, too lazy to close the blinds. But you can see these little sort of knurly things. Just about make them out. Yeah, these are these photodiode detectors. So what happens is this is all coupled to this is the inlet from a column, and this is an outlet from a column. So you've got liquid going through this cell. So your solution passes through the cell. As it comes out the column, it goes through the cell, bigger particles first, smaller particles later. And when it goes through the cell, instantaneously, you've got this laser shining light through it, and instantaneously, these detectors pick up the intensity. So you get these instantaneous snapshots of intensity as a function of angle. And you got the concentration as well from the refractive index detector being measured at the same time. So you get for each volume slice coming through the column, we get this snapshot of intensity against angle. We've got the concentration, so we can work out the molecular weight of everything that goes through the column. So it's great. The columns separate, and the light scattering instrument measures the molecular weight. And it's a great combination because light scattering by itself is not very good at handling mixtures of molecules. So polysaccharides, which got all sorts of stuff in there, mixtures of protein, dimers and trimers, all this sort of stuff. Light scattering struggles to pick up the molecular weights properly. But if you've got online something which is separating the molecules out for you, brilliant. So light scattering's happy, and the chromatography is happy because it can't measure molecular weights absolutely because it hasn't got the calibrations, but the light scattering's doing it for you. So it's a great idea. By Wyatt Technology, and deserving of a Nobel Prize. Again, what? No. And this is what you can do. This is our lab actually. So again, boxes. That's the multi-angle laser light scattering. These are the columns here. They're normally in a thermostatic cabinet actually. So when you go into our lab, you'll just see a cabinet and the columns are in there. That's the this is the concentration detector here, and this is a. Can you read that? No. What you got? You're young. You got better eyes than me. Anyone can see that says viscous star. Okay, Viscostar, which is a viscosity measuring device. So we can measure, as well as molecular weight, we can measure Rg, providing the molecules are larger than 140,000. And we can also measure the intrinsic viscosity, because this measures the intrinsic viscosity of material that comes through the column. Right, here's some plots. This is these are mucin molecules that have gone through the column. This is a native mucin. We'll do mucins next semester when we do the polysaccharide and drug delivery module. When we talk about include things like mucoadhesion for drug delivery and things, and how we characterize these mucins, which are these large. I mentioned these large glycoproteins, and but there is love that makes the world go round. It's mucus and slime, which keeps it in perpetual motion. So nature's natural lubricant. These large molecules. See the distributions of molecular weight, very broad, and these have been treated with disulfide bond reducing agents and also enzymes. Yeah, and this is the third detector, which is the viscosity detector. And it means you can get distributions of viscosity as well as distributions of molecular weight. This is a mixture of 4 polylan polysaccharides. And the column has separated the components out. 1, 2, 3, 4. And the light scattering has measured their molecular weights. 1, 2, 3, 4. Look, very small molecular weight here. And the viscosity detector has measured the intrinsic viscosities. 1, 2, 3, 4. And from how the viscosity changes with molecular weight, we can get the confirmation by, what was that equation which linked the intrinsic viscosity with molecular weight? MHKS, that's right, the Markowing-Kuhn-Sakurada equation. Remember the Howe triangle? Yeah, good. So this is a nice piece of kit when it works. This is a nice piece of kit. It really is. And that's why it's so popular in the biopharma industry. Obviously, the bigger companies, the smaller ones can't afford it, sadly, but the larger companies, the GSKs, the Pfizers, all these have got all this sort of gear. In fact, GSK at Rixensart in Belgium, who we work with our glycovaccines project, they've got 5 of these devices. Yeah, greedy so-and-sos, 5. We dream of that. We struggle to keep one going. But that's universities versus industry, isn't it, really? That's why when you get your jobs in industry, these big companies, you're very generous towards people like me later on. When ours breaks down, becoming us favors. So yeah, it's a very, very powerful, very popular method for characterizing the sizes, size distributions, and shapes of molecules. So if you want to know whether your particular material, your antibody or glycovaccine is within or outside a patent specified by somebody else, then this technique and your centrifuge are the 2 methods which are what you should be using. Not chromatography by itself, because it has no absolute basis, it needs calibrating. So there you are, that's what you need to, obviously it's more complicated than that. The theory, if you want to go into it, is much more complex, but that's just enough for you to be able to understand how the system works. And what bibliography? There's that. You're going to go to Wyatt's website. He's a great bloke, Phil Wyatt. And this book. This is a good book, this. But sadly, it's now out of print. It was out of print a few years ago. But there's still copies in the library. It's based on a meeting we did in Cambridge in 1990, I think, before you lot were born. So yeah, follow up, go to the Wyatt website, and you can get this book in the library, chapters by Wyatt and Rhymes. That's it, folks. So that's Sec MALS. If you want to have a look at the gear, then just pop over to the Lines building and you can see it, but basically it's captured on the computer. So, just for your course reps, you are going to find out who hasn't. No, it's Abby's as well. For sure.
Well, there's only 4 left, so it's improvement.
There's 5 left.
Oh, I will hear, yeah.
Toby. So Toby, Herbert, Dylan. Dylan's done it, I think.
No, totally, I'm pretty sure.
Just, who else is there?
I'll get back to you.
Okay. We've had this before actually. We've had Christmas dues where there's one or two presents had been bought.
So do you get those back?
Yeah, we have some contingency ones just in case. We've also had some, in terms of suitability, we regard it as sort of borderline presents have been bought as well in the past. So use your discretion.